So now we're going to start having a look at the Wilcoxon signed rank test. This is similar to the signed test that we've already had a look at, but it's got a few key differences. So the Wilcoxon rank signed test works similar to the way the signed test works. So it is non-parametric and distribution free again. However, this time the size of the difference between the individual items of data is taken into account. That means that it's got some key advantages. So the advantages are that as the size of the difference is taken into account, the result found has a higher reliability. There is a disadvantage as well, which is that it is more time consuming. Also, the Wilcoxon signed rank test does have a few assumptions that go along with it. So in the same way as we had the paired signed test, we are also going to have the paired Wilcoxon signed rank test. So if the data is paired, it has to come from the same population. Again, each pair has to be chosen at random and independent, but most importantly, we can only perform the Wilcoxon signed rank test with single sample data or paired data if the data follows a symmetrical distribution. And this creates a nice scenario where the mean and the median are the same. So the question could be talking about the mean or the median, but that is only because the data is symmetrical. Now, it's quite important that you know the difference between the Wilcoxon signed rank test and a normal hypothesis test. In a normal hypothesis test, for a small sample, which will only have small samples when we're doing the Wilcoxon signed rank test because they're not going to want you to find over 30 differences, if it doesn't mention that the population is normally distributed, or it may even specifically tell you that the population is not normally distributed, that means that we are performing a Wilcoxon signed rank test and not a normal hypothesis test. So you need to be careful and look out for that. Also, the data in the paired Wilcoxon signed rank test is obviously paired data. So again, it's not appropriate to do a two sample normal test, which comes up in A2 statistics. So we're going to first have a look at what we do when we have a single sample. Now this is where it differs from the signed test, because this time our critical value is going to come from the formula booklet. We're going to have a look at the number of pieces of data put together in the same way as we did with the PMCC and the SRCC. And it's going to be, the critical value comes from this table in your formula booklet, which is on page 25. Again, be careful, make sure you read carefully at the top what the test is for. This is the critical values of the Wilcoxon signed rank test statistic. So you've just got to be careful and make sure you are looking at the correct table. So we're going to have a look at a one-tail test to begin with. So here we have 11 job applications are randomly chosen from a large group and asked to attend an interview, during which each applicant takes an aptitude test to identify who would be best suited for the job available. The mean score nationally is known to be 64. The mean scores for the most recent applicants are here. Test the hypothesis using a 5% significance level that the group of applicants have a lower aptitude than found nationally. Now, it's quite important that we pay attention to the fact that we are talking about the mean, but at no point does it state that these are normally distributed, and at no point does it give us a standard deviation. So that means that this is a Wilcoxon signed rank test. So our H0 is going to be that the median is the same as the population, 64. We write our hypothesis in the same way as we did with the sign test. So then we're having a look if it's lower than nationally, so lower than 64. Again, this is where it becomes different. We're going to make a table with these values in there. So we're going to have the data, which is 56, 57, 62, 64, 62, 66, 56, 65, 69, 60 and 61. We're then going to have the difference, and you need to make sure that you're doing the take away the same way for all of these. Now I'm going to do 64, I'm going to do the piece of data minus 64. You could do 64 minus the piece of data, just as long as you're consistent all the way down. So 56 minus 64 gives me minus 8. 64 minus 57. 57 minus 64 gives me minus 7. And we're doing the same all the way down. If you don't want to do it all in your head, you could use the normal calculator bit of your calculator. Or, as shown in the sign test video, we can get our calculator to do it in the statistics function. So we're going to do 56, type the data into the calculator. So 56, 57, 62, 64, 62, 66, 56, 65, 69, 60 and 61. Just double check that I've put all those in correctly. And then if we go to the top where it says list 2, make sure that you have the list 2 bit highlighted. And then we need to go shift and then 1 to make it say list. And we want to do list 1 minus 64. Sorry, I forgot to just double check that I've entered all them in correctly. I think I have 62, 64, 62, 66, 56, 65, 69, 60, 61, yes. And then my differences are all in my list 2 now. So like I said, you can do it in the normal calculator bit. You can do it in your head if you want. But as long as you're right, or you can do this method here that I've just shown you, as long as you write down your differences. Now in a similar way again as we did with the sign test, anything that gives us the answer of a difference of 0, we're going to put a dot. So then minus 2, 2, minus 8, 1, 5, minus 4, minus 3. So now that I have all my differences, we need to rank those differences. Now, when we are doing our ranking, we want to split them into rank pluses and rank minuses. Now, rank pluses are going to be for when I rank a piece of data that is positive. Rank minus is going to be for when I rank a piece of data that is negative. When I do my ranking, it's just going to be the size of the difference that I take into account, not the actual value. So the smallest difference from 0 that I have is 1 here. So for the rank of 1, 1 is positive, so that gets the rank 1 in the positive column. So the next biggest difference I have is 2, but I have a 2 and I have 2 minus 2s, and they are all the same difference away from 0. So in the same way as we do with the Spearman's rank correlation coefficient, we want them all to have the same rank. So that's the rank 2, 3 and 4 being split between 3 numbers, which means that they're all going to get the rank 3. So this first one here, minus 2, gets the rank 3. The next one here, minus 2, also gets the rank 3. Notice how both of those ranks went in the rank minus column. But this one here, 2, is going to get the rank 3, but this time that's going to go in the plus column. The next biggest difference I have is minus 3. So 2, 3 and 4 have gone. So 5 is the next biggest. And again, it's a negative number, so that needs to go in the rank minus column. Then minus 4, that's going to get the rank 6, again in the negative column. Then 5, which is positive, so that gets the rank 7 in the rank plus column. Then minus 7 is going to get the rank 8, again in the negative column. Then I have 2 minus 8s. They're going to get the rank 9 and 10. Divided by 2 people, which means that they each get the rank 9.5. This 8 is negative, so the 9.5 goes in the rank minus column, and this 8 is also negative, so that gets the rank 9.5 as well. So you can see clearly which ones have been ranked negative numbers and which ones have been ranked positive numbers. It's also very important that you start off with the numbers that are closest to 0 when you are doing your ranking. So the next step here is to add the rankings together for the pluses and the minuses. So the total for the pluses is 3 add 7 add 1, which gives us 11. And the total for the minuses, I'm going to have to put this in my calculator, sorry, is going to be 9.5 plus 8 plus 3 plus 3 plus 9.5 plus 6 plus 5 and that gives us 44. Now, as a way that we can check this, in the formula booklet there is a formula on the critical values page. The formula looks like a half of n, oops, sorry, there's not a bracket there, half of n plus 1, and that should give you the total of the totals. So n is the number of pieces of data that we have. We have 11 pieces of data here, so it's going to be a half of 11 times n, sorry, we've knocked one of those off because we actually only have 10 because we're not counting this one anymore. So it's going to be a half of 10. 10 plus 1 is 11. A half of 110 gives us 55. And when we have a look here, 11 plus 44 does give us 55. So we have done our ranking and totals hopefully corrected. So then, the smallest of those two totals is our test statistic. So that means that our test statistic is going to be 11. And we're going to get our critical value from the table which I described before. So remember that the number of pieces of data that we have is 10 because we are not counting this one here that had a difference of 0. So we have 10 pieces of data and it's one tail at 5%. So if we get our table up, one-tailed, 5%, 10 pieces of data, we can see here that the critical value is 11. Now this is the first time that we've come across an example like this, where the critical value is the same as the test statistic. So this brings up an important point as well, that the critical value is the first value at which you reject H0. So as the test statistic is equal to the critical value, we are still going to be rejecting H0. So as the test statistic is equal to the critical value, we reject H0 at a 5% significance level. There is sufficient evidence to suggest, and that's that the applicants have a lower aptitude on average than nationally. Now, if they weren't equal, we need to know what we're going to do with them then. Well, the whole point of this test is to see if the totals differ by enough. So if the test statistic, so the smallest of the differences, is smaller than our critical value, that is when we reject H0, because that means that there is a big enough difference between our rankings so that then we are saying, actually, there is a difference. If the test statistic is bigger than the critical value, so the smallest of our totals is bigger than our critical value, then we end up accepting H0. And this is because when we're looking at this, that means that our totals for the rank plus and the rank minus are close together, meaning that there isn't a big difference between the two sets. I'd now like you to pause the video and give the Now You Try a go, being careful with the values here, and also we're trying to see that the journalist believes that the new shopping centre is an asset. So if you have a look here, the question is, the newly opened shopping centre is an asset to the town. You want people to be in these three numbers here. So you need to think about how you're going to get that across. Okay, so hopefully you paused the video and gave the Now You Try question a go. So as we were saying, this has a journalist is asking customers to agree or disagree with a statement that the newly opened shopping centre is an asset to the town. So we're wanting, if they have no opinion, then it's going to be 4. So our H0 is that the median is 4. We're wanting them to agree with the statement. So we're wanting the median to be less than 4. That's what we're testing. So the journalist chooses 12 people at random to form a data sheet, and the responses were there. And then the journalist believes that the new shopping centre is an asset. Test this hypothesis using the Wilcoxon ranked sign test at a 10% significance level. So then we have our values here. I've just rewrote them. We have our differences. Again, I've done the piece of data minus the median that we're testing. You can do it the other way around as long as you do all your takeaways the same way round. We have a lot of 1, 2s and 3s, ignoring the signs, because of the range of data that we're looking at. So then we have, for the 1s, we have the 1 at the top, we have 1 here, we have a -1 here and a -1 here. So we have 4 1s, so they're going to get the rank 1, 2, 3 and 4. Divided by the 4 different numbers means that they each get the rank of 2.5. Then for the 2s, we have a -2 here, we have a 2 here, and we have another -2 here. So they get the rank of 4's already gone. So 5, 6 and 7 divided by 3, because there's 3 of those, which means that they each get the rank 6. And again with 3, they get the rank 8, 9 and 10. Divided by 3 means that they all get the rank 9. And you can see those here. Then when you add those together, we get 11 for the plus, 44 for the minus. This time, however, it is a 10% significance level. So if we go back to our table, one tail, 10%, 10 pieces of data gives us 14. Again, we've got 2 dots in this data. Sorry, wrong way. We have 2 dots in this data that we won't be counting, which is here and here. So we do have 10 pieces because we're not counting those 2. So that means that this time our critical value is 14. So as we talked about before, as the test statistic is less than the critical value, this time we end up rejecting H0. At 10% significance level, there is sufficient evidence to suggest that the average opinion is less than 4. And then I've added a little sentence there, meaning that the shopping centre is an asset, to refer back to what they were asking about in the question. So we're going to have a quick look at the two-tailed tests. This is still with single sample. So for two-tail, you're still looking at the same table, but when you're looking up the significance level, you look at the second row, which I've put a box around here, instead of the first row. So we're going to have a look at an example. So here we have the median lifetime of a certain brand of battery is claimed to be 300 hours. A random sample of 15 batteries is taken and the lifetimes are recorded. Use a Wilcoxon rank sign test at a 5% significance level to test the claim that the median is 300 hours is justified. So that means it either is going to be 300 hours or it's not going to be 300 hours. So our H0 is that the median is 300. Our H1 is going to be that the median is not 300. And then we're going to have to write our values and our differences, and then our rank plus, and then our rank minus, in the same way as we did for the one-tail tests. So we have 3, 4, 2. I'm going to work across, going to try and write as small as I can to fit it in. 302, 393, 265, 289, 257, 216, 312, 339, 402, 249, 306, 190 and 178. So this is quite a lot of numbers this time, and we're still having to find the difference. So I am going to do this in my calculator again. Remember to delete anything that you've already got in there. Type the values in the same way as you have wrote them down. So I wrote them down going across, so I'm going to enter them going across. If you wrote them in down going down, make sure you enter them going down. So we've got 3, 4, 2. 278, 302, 393, 265, 289, 257, 216, 312, 339, 402, 249, 306, 190 and 178. Just quickly double checking that I've entered all those in correctly. Again, whenever you're putting anything into your calculator, always double check, because we're going to get our answer from the calculator, and if we've typed something in wrong, we're not going to get the marks. So then at the top, make sure you have list 2 highlighted like this, and we want to do list 1. So remember, shift and then 1 to get the word list up. 1 minus, this time, 300. And all the values have come up there, so I can just write those down. So we've got 42 minus 22, 2, 93, minus 35, minus 11, minus 43, minus 84, $12, 39, 102, minus 51, 6, minus 110, and minus 122. So when we're looking at the differences, the smallest difference is 2, so that's going to get the rank 1. So I've done that one. I'm going to put a tick next to them this time so I can see which ones I've done. The next smallest one is 6. That's going to get the rank 2. The next smallest is minus 11. So that's going to get the rank 3, but in the minus column. Then 12, which gets the rank 4, but in the plus column. I think that's everything in the single digits and teens yet. Looking for 20s, minus 22. It's going to get the rank 5, but in the minus column. Then 30s, 35, minus 35. That's going to get the rank 6 in the minus column. Then 39, that's going to get the rank 7 in the plus column. Then 42, that's going to get the rank 8 in the plus column. Then 43 is going to get the rank 9 in the minus column. Let's have a look at what we've got left. We've got 93, 84, 102, 51, 110. So it's 51 next. So that's going to get the rank 10 in the minus column. Then 84, yep, is going to get 11 in the minus column. Then 93 is going to get 12 in the plus column. Then 102 is going to get 13 in the plus column. 110 is going to get 14 in the minus column. And finally, minus 122 is going to get 15 in the minus column. So it does still take some time. Another way that you can do it to help you is that if you go to the top of list 2, once you've put all your differences in there, if you go across, so once you've got list 2 highlighted like this, and you can go to Tool, and then you can sort into ascending order. List, how many lists? One list. Which list do I want to do? List 2. And it comes up like this. Now the issue with this is that it hasn't taken the sign into account. So you could, if you wanted to, take all the negatives off first, and then you'll have to refer back to your data to see which was negative and which were positive. But it's just ways that you can try and help yourself with the ranking. So in the same way as we did with the one-tail hypothesis testing, we're now going to total our rank pluses and total our rank minuses. So in the normal calculator bit, I'm going to add these up. So we have 8 plus 1 plus 12 plus 4 plus 7 plus 13 plus 2. So 8, 1, 12, 4, 7, 13, 2. That gives me 47. And then 5, 6, 3, 9, 11, 10, 14, 15. That gives me 73. If you think about that formula that I told you about on the critical value page, we have 15 pieces of data here. So that would be a half times 15 plus 1, which is 16. Do these add up to 120? Well, 47 plus 73. Yes, they do. So I might have done these. I've probably done these correctly. Again, the smallest total is our test statistic. So our test statistic is 47. Our critical value we're going to get from the critical value table. Remember to look across from two-tail this time. So two-tail, 5% and 15 piece of data. So two-tail, 5%, piece of data 15. So we've got 25. So our critical value is 25. And the conclusions are drawn in the same way as with the one tail. So as the test statistic is bigger than the critical value, this time we're going to accept H0 at a 5% significance level. There is insufficient evidence to suggest the median, and this is battery lifetime, is not 300 hours. So I'd now like you to pause the video and give the Now You Try question a go. Okay, so hopefully you paused the video and gave the Now You Try question a go. So now we've got the new recruits to a call centre are given an initial training in answering calls. Following their training, they are independently assessed on their competence and and are rated on a score of 1 to 10, 1 representing total incompetence and 10 representing total competence. This is usual for it is usual for the trainees to score to be symmetrical. So that tells us that we're using the Wilcoxon rank sign test with a median of 6. A new trainer has been appointed and the scores of her first 19 trainees are there. Is this evidence at a 5% significance level that the new trainer has changed the trainee outcome? So we're saying if the median is still 6 or the median is not 6, so our H0 is that the median equals 6, our H1 is that the median is not equal to 6. And I haven't had enough room to fit my titles on there. I've just about managed to fit it all in here. So you can see that the 6s have got dots, the 5s, the 4, you can see all the differences there in red and green, just to make it a bit easier for me to see. Again, we had 7 1s or minus 1s, so they all got the rank of 4. We had 3 2s, which all got the rank of 9. We had 4 3s, which all got the rank of 12.5. And we had 1 minus 4, which got the rank of 15. When we added those totals together, we got 62.5 and 57.5. So the smallest of those is our test statistic. So that's 57.5. The critical value is 25. So as the test statistic is bigger than the critical value, we end up accepting H0 at 5% significance level. There is insufficient evidence to suggest that the average score of the trainees is not 6 with the new trainer. Now, it's quite important to understand that just as the PMCC and SRCC are tests that go together nicely, it is the same with the Wilcoxon sign rank test and the sign test. So if it specifically mentions that one of them isn't appropriate, or which one would have been a better choice, or what other test could you have done, if you're already doing the Wilcoxon rank sign test, then it's a good idea to mention the sign test and vice versa. So next time we're going to have a look at how to do the Wilcoxon signed rank test with paired data. Thank you very much for listening.